Okay, I thought I would take a second here just to make a quick video on the what we call the equation method of error propagation in the lab manual. Okay, and I'm going to discuss this method of error propagation in the context of the calculation that we did in the third lab where we're dealing with a pendulum. Okay, so I'm going to go over this kind of slowly for anybody who might be having issues here, and this will sort of be a reference that you can use if ever you're unclear on how to use this error propagation method. Okay, so everything that I'm going to say here is basically covered on pages 14 and 15 of the lab manual, and the experiment that I'm going to be referring to is experiment number 3, which is on page 23 of the lab manual. Okay, and so let's start off. When we talk about the equation method of error propagation, we're talking about one specific way to propagate error. There's other ways to do this. We've talked about the brute force method. This video is not going to be about the brute force method. I'm only talking about the equation method here. Okay. And so what does the lab manual tell us about the equation method? Well, we start off with this expression at the top of page 14 of the lab manual, where we're told that that for some, and I'm going to write it like this, for some expression that looks like this, we can solve for our uncertainty, our error, our delta y in the following way. And we end up with this expression here. Oops. Okay, and there would be a more concise way to write this and stuff, maybe for both terms. But in the end, this sort of gives us the guideline on how we're supposed to propagate error in, well, using the equation method. And so maybe I'll take a quick step back here. Okay, so why would we even want to use this error propagation method, right? We use this error propagation method when we have an equation that relates some quantities that we know that have error associated with them already. And when I say error, I mean uncertainty associated with them already, and we want to propagate this error into this new quantity that we're calculating. So let's take a look at this in the context of the experiment number 3 calculation. Okay, so in experiment number 3, we did this. We were working with this pendulum, right? And we're told that for the period of a pendulum, large T, right? And I'm not going to write down what all these variables are, but you can see what they are on page 23 of the lab manual. That we have this expression that relates the length of the pendulum, our gravitational acceleration, and the period of the pendulum, right? So in that lab setup, and I guess depending on when you're watching this video, maybe you will have done this lab or maybe not. But in this lab, or in this experiment, we're solving for g first, because we're going to be calculating g. We're going to measure L, and we're going to measure capital T here, which is our length and our period again, and we're going to calculate what g should be. So what do we do here? Well, we solve for g, and maybe I'll just do that very quickly, right? So the way I would do that is just square both sides. So we're going to end up with an expression that looks like this, right? And then just isolate g, right? So I'm just going to isolate g. I'm going to multiply both sides by g and divide through by a t squared, right? So we're going to end up with something that looks like this. We're going to have 4 pi squared here and an L over t squared here, right? And that's great, except I'm going to rewrite this one more time. That's just going to make it very, very easy for us to apply this equation method of error propagation to this equation, right? So let me rewrite this one more time. I'm going to rewrite it like this. G is going to be equal to 4 pi squared. I'm just going to put that in a bracket. Then I'm going to have L, and I'm going to put L to the power of 1, right? Basically, we can do that to whatever we want, right? Putting things to the power of 1 doesn't change them. And then I'm just going to move my t upstairs, so it's going to be to the power of -2 instead of 2, okay? So this is the equation that's going to be the easiest for us to work with to apply this equation method. Okay? And so if we look at this equation here, it looks a lot like this equation up here, right? It's just an equation that has a number of variables to some power. And what are we doing in the lab? So in the lab, what we do is we measure L. We end up measuring L, so this is a measured quantity, and we end up with some L. We do it for a couple of different lengths, but let's say, for example, we only did it for one length. We end up with some L plus or minus some delta L, right? And in the lab, we also measure some T. We do this by watching the pendulum swing a number of times, and then we divide out the number of swings and so forth. But in the end, we end up with some T plus or minus delta T, okay? So we have these two measured quantities, L and T, that have their associated uncertainties, and we want to find what the uncertainty in G is. Okay, so we're going to calculate, we can just stick in this L and this T into this equation that we've calculated, and we're going to find some G. But we also want to find the associated uncertainty with that G. So how do we do that? Well, there's a number of ways to do that, but the way that we're going to talk about doing that is using this equation method of error propagation. Okay, so let's translate this equation into the form that we see here. Well, we've already done that. We've already translated it into that form, but let's identify what the variables are, right? So in this picture over here, what is y ends up being g from what we have over here. So basically what we're saying is, to translate between these two, we have g on this side. Well, g is just going to be what we call y over here. K, what we call k over here, well, this is a constant, right? So I didn't mention it here, but in the lab manual we do mention it. K and all of the AI, maybe I won't write it like that. Maybe I'll say k and A1, A2, A3, and all the A's, all those powers. These are all constants, right? So k is just some constant, and in our equation for g here, we do have a constant. We have this 4 pi squared. That's a constant, right? And so that's going to be our constant. We also have L on this side, and L we can just designate that's what x1 is. But if L is x1, then A1, the power of L on this side, and I shouldn't write it like that, the A1 would be on this side, would just be 1, right? We're just looking at this power, the power to which L is raised, right? So we have a 1 there. And again, so what's x2 over here? Well, x2 will just be our t, and a2 will just be minus 2, okay? So if we think about sort of translating this equation on the right into this equation on the left, well, now we can just start substituting in, right? And this is what leads us to our uncertainty in G, right? So let's take a look at what our uncertainty in G will be. Okay, so I'm just going to copy down this expression up here, this star expression, in terms of the variables that we've just defined on the right over here. Okay, so we're going to end up having delta G, and that's a terrible looking delta, so delta G over G squared is equal to, well, what's A1? That's just 1, so I guess I can write it here, 1 times our delta L, right? So we're going to need some delta L over what's x1, well, that's just L squared, plus what's A2, well, A2 is minus 2, it's the power to which t is raised, so it's just minus 2 times delta t over t squared. Okay, and this is basically it, right? So to be able to complete this whole operation of propagating the error, we will have already needed to have calculated or found what delta L and delta T are. Now these are both measured quantities, and again, depending on whether you've done experiment number 3 or not yet, you may or may not know what I'm talking about here, but we will have measured L, right? So we'll have measured L, and we'll have assigned an uncertainty to L. So we're measuring some length, the length of the pendulum, right? And we're going to assign some uncertainty to it. You're going to do this either by looking at the systematic uncertainty that we have in there. We're going to have our instrumental and observational uncertainty, and then we're also, well, in this case we're only making one measurement, right? So In the case of delta L, it's just going to be the total of those two values. But in the case of delta T, we're going to have a number of different times. So we're going to have our observational and instrumental uncertainties added together to give us our total systematic uncertainty. But on top of that, we're also going to take a look at random error. But all that is beyond the scope of this video. Basically, all I'm saying is that at this point, we'll have already calculated delta L and delta T. So they're just going to be inputs into this formula. And basically, at this point, we're just wanting to solve for delta G. So I'm just going to isolate delta G very quickly. And so the first thing we would do is take the square root of both sides, right? But we would end up with a plus or minus. We don't really need to worry about that because this delta G is an uncertainty, so it naturally comes with a plus or minus, right? So normally when you take the square root of both sides of something, you need to be careful about whether you're picking the positive or negative root, right? In this case, we're kind of picking both, so we don't have to worry about that. But we end up with this expression here. Written like this. And at this point, it's just a matter of substituting in numbers, right? So we sub in delta L here, we sub in delta T here, L here, T here, process the whole thing. We take our G, whatever the G that we calculated using this expression is, and plug it in there, and we simply pull out a delta G. And now once we have this delta G, this is our uncertainty in our G. So from this point forward, we always know what our uncertainty in G is for this calculated G. So anytime we write down G, we're going to write down this G. We'll write G plus or minus whatever value we found for delta G is, right? And this will obviously come in meters per second squared. Okay, so that's just a quick sort of reminder or review on how to use the equation method of error propagation. Again, this is all from pages 14 and 15 in the text, and hopefully this sort of clears it up for some people. If you're having any issues with any of these, or you're not sure how to use this technique, please come and see me, and I will be happy to help you out with that. Okay? Thank you very much.